All right, good morning, everybody. Welcome back. Today, we're going to keep talking about sorting algorithms. We'll finish implementing insertion sort, and we will talk about another sorting algorithm that actually achieves best case performance in the common case, or in the worst case, sorting arrays. We're also going to pause in the middle and introduce a new Java feature. This is something that we'll kind of keep doing throughout the remainder of this semester. As we talk about algorithms, as we keep talking about data structures, we'll, from time to time dive back in to show you a little bit more about how Java works. So that's a plan for today. Before we get there, I just want to pause and talk a little bit about where we are in this semester, how people are doing. So here's the thing. I was thinking about this yesterday. I was a college freshman 20 years ago. Feels like a long time. So I've now lived more than half my life after being a freshman in college. But I have some memories, believe it or not, of freshman year in college. I remember it felt like it was just a long time until Thanksgiving came, and that is still true. Unfortunately, we haven't been able to move Thanksgiving on the calendar. We have 1 week left, so you guys are almost there. But this is a point in the semester, I think, where, it's been a long couple of months. You guys have been working really hard. We've been cranking up the difficulty a little bit this week on the MP, on the homework problems. Some of you are also discovering, as I discovered 20 years ago, that you are not the smartest person here. A lot of you came from schools, high schools, where you probably were one of the smartest person at the school. I certainly felt like I was when I was in high school. My high school wasn't necessarily super competitive, but I remember arriving in college and suddenly, like many of you, feeling like I didn't belong. I was surrounded by people, all of whom seemed definitely much more intelligent than I was. And then, of course, you fall back to thinking, well, they're probably assholes, right? Like, there's probably something wrong with them, Like, they're probably mean, they don't have any other interests, all they do is study all the time. And then you start meeting them, and you're like, oh, actually, they're really nice, and they're interesting, and they're kind, and they do all sorts of other cool things. And they just seem like, I just feel like I'm a subset of them. Like, they do more of everything than I do. Like, how am I ever going to accomplish anything? Why am I here? My brother, when my brother applied, my mom's gonna be mad at me for telling this story. When my brother applied to college, my mom, she told me, you should go into the admissions office and tell them that they should admit him. Like, that's not how admission works anywhere. And I remember thinking, no, you don't want that. Like, you do not want me going there and reminding them that they admitted somebody from our family and connecting them to this other person. That is not gonna work out the way you think, right? Neither my brother or sister got into the same school as I did, probably for that reason. They were like, we made one mistake on the Warner Allen family, we're not making others. Anyway, but I know that it's natural to feel this way right now. And again, it's getting cold outside, it's dark, everything just there's this gloom that seems to be descending. So I just want to remind you that these feelings are normal. This is happening to a lot of people here. Some of you are hiding it better than others. But I think many of you are feeling this way. That's okay. It's normal. We took a bunch of really smart people, and we brought them all to one place. And what you're gonna find over time is that this tends to work out really well. You guys are gonna learn from each other, you're gonna inspire each other. You're not competitors. You guys are colleagues. And the fact that there's other smart people in this room is something that is going to help you in the future. These are people who are going to improve your life in a variety of different ways, and there is plenty for all of you to do in the world. There's no shortage of work and good problems to solve and things to fix and ways to improve the world for all of you. There's definitely enough to do. So just keep that in mind. Again, very common to feel this way at this time in the semester. You're all here for a good reason, and go ahead and make the best of this opportunity. And there's 1 week left into Thanksgiving, at which point you can rest, relax, and come back motivated to finish up the class, your final projects, which I'm really excited to see. Okay, end of pep talk. let's talk about yesterday's homework problem. All right, so this was a good one. One of my favorites this semester. I think people struggle with this, so let's go over this. So another one in our series of recursion problems on trees, and the goal was to determine if the tree was balanced. What is a balanced tree? A balanced tree is a tree where if I look down at both my subtrees, the height of those two subtrees doesn't differ by more than 1. A tree being balanced, why would I actually want to know this about a tree? Well, when you guys get down to 225, you'll discover that certain algorithms, and we may talk about this semester as well, certain algorithms that we run on trees, like looking for a node in a binary search tree, do really well if the tree is balanced. They run in log n time. Once the tree starts to get extremely imbalanced, then they start to run in more like O(n) time. So it's almost, you can imagine an incredibly imbalanced tree is essentially a linked list that I just turned on its side. So I get none of the benefits of the tree structure. Okay. So how am I going to do this? Oh, and let me point this out. A balanced tree also has to be balanced at every node. So it's possible for a tree to be balanced at the top, but then once I start looking down farther, I find an unbalanced portion of it. So this is a property that I need to check at every node. So how are we going to do this? So what's the base case here? Yeah. Yeah, when I get to either a leaf node or in the implementation, when I get to an empty tree, when I walk off the bottom of the tree. An empty tree is balanced. Okay? My recursive step, as I frequently do when I solve these problems, is I look at my right and left tree separately. So I'm making the problem smaller by saying, okay, I'm going to, split this problem into 2 smaller pieces. I'm gonna try to figure out if the tree is balanced from where I am, but then the tree, in order for the tree to be balanced, both my left and right subtrees also have to be balanced. And then I'm gonna combine results by, there are 3 things that have to be true at every node. The first is the tree has to be balanced at that node. The second is the right subtree has to be balanced. The third thing is the left subtree has to be balanced. So I apply this recursive algorithm, this is going to work. As you start, so let me just walk through this with you. So I have, in order to get this example to work, I have created a new version. Well, I've done 2 things. First of all, I've broken our original add function. I just want to point this out because I don't want someone coming back later and thinking this is the right way to add nodes to a tree. I've broken this so that if a node is full, it always adds things to the right subtree. This will very quickly create an unbalanced tree. So this is what we're going to use to make sure that our algorithm is correct. I've also added a second function to add nodes to our tree called balanced add. What does this do? So this function creates a balanced binary tree. How does it do this? Well, at the top, I'm doing the same thing that I did in my original add function. I essentially say, if there's space at this node, I either add the new node as the right or left child of the node that I'm at. But if there's not space at this node, what do? Well, what I want to do is I want to add it to the subtree that has the shorter depth, or the shorter height. So this will make sure that as I'm building the tree, I maintain the balance property that I want. So when I get down here, I say, if my left subtree is taller than my right subtree, then I'm going to add the node to my left subtree. Otherwise, I'll add it to the right. So by doing this, as I build up the tree, and I wish I had a diagram to show this, but I don't, I'm going to fill it in a balanced fashion. So this will build a balanced tree. Okay. But what do I need to get this to work? There's a missing function in here already in my balanced add implementation. What do I need to be able to compute for this to work? The height of the tree. And I don't have a function to do that yet. So this was one of the things that was fun about this problem. I have another recursive problem to solve, which is the height or depth. We were talking about it as depth before, but height is another term for it, of a tree. So what is the height? The height is the distance to the furthest leaf node from a particular node. So how many levels do I have to go until I get to the furthest leaf node? How do I compute this recursively? So, as usual, I'm going to think about first my base case. So, when I've reached a null node, then the height of the empty tree is 0. My recursive step is I break the tree into two parts, as I usually do. And how do I combine the results together? I return the maximum of the height of either my right subtree or my left subtree. So the height is the maximum number of levels I have to go down before I get to the leaf. So let's implement height first, because I need this for my add function. So I'm going to create a private function called height, and I'll let this do this from the current node. So what's my base case? Always want the base case on top. When do I stop? What do you think? Well, let's do it till I hit null, right? I could try to test for a leaf node. This is one thing I've seen on a lot of your recursive implementations. They get too complicated because you don't handle null properly, and so you start poking around in the right and left subtrees. But I don't need to do that, actually. What I'm gonna do is I'm gonna say if current is equal to null, then I'll return 0. Otherwise, what's my recursive step? Yeah. So I'm going to take the maximum of my left and right subtree, and then, critically, add 1, because I'm counting myself. So this is sort of a nice, clever way of combining these three pieces of information. 1, that's me, maximum of my right subtree and left subtree. Okay, so once I'm done with this, I need to put a dummy return statement in here. But at least my balanced add function will now work, which is good. Okay, so I have my height function. I can build a balanced tree. Now let's come back to the height balanced problem and do that one. So I'm going to, that function is going to serve as a wrapper, calling my recursive function on the root node. What's my base case? Similar to usual, yeah? Reaches null, in which case I return what? An empty tree is balanced. Yep. Otherwise, I want to, so here was where we gave you a hint. I don't know if my right subtree is taller than my left subtree, but what I'm interested in is the difference. So what I'm gonna do is I'm gonna say I'm gonna compute the difference between current.right I need to be able to type. I'm going to take the absolute value of the difference between the two. When is my tree not balanced? So now I know the difference between the height of my right subtree and the height of my left subtree. What am I testing against to decide if the tree is balanced? So it's okay for them to differ by a little bit, but they can't differ by more than 1, right? Okay, so I'm going to say if, so there's 3 things that have to be true. First of all, the tree is balanced from this node, so that's what I've just tested here. I'm computing the height of my right subtree, the height of my left subtree, I'm taking the difference, I'm computing the absolute value, so I don't have to have a really complex conditional, and I'm testing if that's greater than 1. Sorry, it should be less than or equal to 1. So if they're the same height, or if the height differs by 1, then the tree is balanced. Otherwise, I need to check 2 other things. What are the 2 other things I need to check? So now I know the height is balanced from this node, left and right side. Yep. So I say if height balanced current.right, and height balanced current.left. So base case here, and then here's my test for whether it's balanced at this node. Remember how short circuit execution works with an AND statement. If that's false, I won't even execute the rest of it. So this is nice. If the tree isn't balanced from the root node, then I should stop immediately. Otherwise, I keep going. I test my right tree, I restart the recursion. Let's have this actually call my wrapper function on the root. Let's see if this works. Okay. So I've created my constructor now takes a new argument telling it whether or not to build a balanced tree. Now it's possible, even if I build a random tree, that it will be balanced just accidentally, but it's usually, well, actually, sorry, I'm not building the tree randomly anymore. I'm building it unbalanced on purpose. So this is always an unbalanced tree. It looks like my function does the right thing there, returns false. Let's build a balanced tree, returns true. Questions about this? So when I've been looking at code that we have been reviewing on the forum, you know, I see a lot of just really long, verbose solutions that are testing the right child and testing the left child and things like this. You know, you typically, particularly when you do it this way and you handle no, you don't need to do that. Right? I mean, a lot of people solved this problem, but a lot of people had a lot of unnecessary machinery inside their solution, right, that they didn't really need. Questions about this before we go on? We have one more of these problems today. It's another little twist, and then we will be done. I also want to point out, which is that these tree recursion problems are harder than the ones that will be on next week's quiz. So just keep that in mind. Also more interesting. Okay, so we've done this. Let's go back to talking about insertion sort. So insertion sort and merge sort, we'll see how far we get, are our topics for today. And let's remind ourselves about how insertion sort works. So insertion sort divides the array into two parts. A sorted part, which starts out as an unsorted part, which starts out as the entire array, and a sorted part, which starts out with one element or empty. And in each step, what I'm doing is I'm moving an item from the unsorted part into the sorted part. So I'm taking, in this case, I'm taking the leftmost item from the unsorted part, and I'm moving it into the sorted part. I have to keep the sorted part sorted, and so when I move that item, I have to make sure it ends up in the right spot. So this is critical. If I do this, however, every step of my algorithm is expanding the sorted part by 1. So the sorted part starts out small and grows by 1 element throughout each step of the algorithm. When I'm done, the sorted part is now the entire array. So the unsorted part goes down by 1 every time, the sorted part goes up by 1. So how do I do this? So in each step, I take an item, and here I'm showing you where that item lands. And depending on what the item is, it might end up, in this case, all the way at the front. It might end up at the end. It might end up somewhere in the middle. So in order to maintain this property of the sorted section, I have to put the item in the right spot. And finally, let's just review from last time. How do I do this? We're about to implement this, so watch carefully. What I'm going to do is I'm actually going to move the item from the unsorted part to the left in the sorted part until I find the right spot. And I'm going to do this by comparing it over and over again against the next item in the sorted section. If this item needs to keep going left, I'm going to swap the two. At some point, I'm going to get to an item that's smaller than it, and that's the right spot. And then at that point, I can stop moving the item to the left, drop it into place, and I'm done. Okay, so let's implement this. So I'm going to go through every element of the input array, and I'm actually going to start with 1, because I can allow if I start with a sorted section of one element, that's okay. A one-element array is sorted by default, so I'm gonna start with my sorted section being of size 1. And then my inner loop is gonna start at I. It's gonna continue while j is greater than 0, and I'll show you why in a minute. And so essentially I'm starting from the first element in the unsorted section, and I'm moving to the left. So what do I do? Say if so what is this check doing? It says if the input array at element j minus 1, so this is an element to the left, is greater than the input array at element j. So this means that I've detected that there are two elements that are out of order. Remember, I'm sorting by default in our examples in ascending order, and so as I go up through the array, I shouldn't find a case like this. Every item should be to the right of items that it's greater than. So if I find this case, then I'm gonna swap them. And this is my sort of canonical way of swapping elements. I store one in a temporary variable, I overwrite that one with the other one, and then I use my temporary variable to move the original value into the other. All right, so let's see if this, it doesn't like this. Oh, whoops, there we go. Here we go, good. This is one of those algorithms that's actually harder to understand when we put it into code than it is to look at. But what's happening here is that, and let me do a little bit of an optimization here. Essentially, I keep looking at pairs of elements starting from, so essentially I'm taking the element from the left side of the unsorted part, and I keep swapping it with elements in the sorted part. And so the sorted elements that are larger than it are moving to the right, and it's moving to the left. Once the condition on line 6 stops being true, I found the right spot for the element, and I can stop. So I can actually break out of the loop at that point. So you can see this produces the same result. Okay, questions about this before we go on? Yeah, for sure. So I'm starting, yeah, good question. So the question is, why do I start at I? Let me see if I can answer this using the diagram. So here, I starts out pointing, referring to this item, right? And you'll see as I'm, other direction. As I'm swapping, I'm moving j to the left. J is going down. So I'm taking the item from the left, the leftmost part of the unsorted section, and I'm moving it left in the array until I find the right spot. So I walk down. Good question. Yeah, this is, again, one of these things that's trickier to look at in code than it is to visualize. Other questions about this? Okay, so this is one of those lectures that has a little bit of everything. Let's analyze this algorithm. So we're back to our big O notation. Time complexity of the algorithm. Let's look at it. What do you see? What are some features of this that you see? Yeah. I see two for loops. I see a nested for loop. Now in this case, of course, the outer for loop is going through essentially the entire array. The inner for loop is only going through I back to the beginning, but, you know, on average, this is still going to be, the for loops are still going to be n squared. What else do I see? So I see two for loops. I can think a little bit about how the indices line up, how many times it's going to execute. What else do I see? Though, that gives me some pause. See two for loops. Yeah, okay, so this part here is roughly constant time, right? These are array lookups. Array lookups are constant time. You do see, however, there's a temporary variable in here. So I have created a temporary variable that I need to use, and we'll come back and point that out when we talk about the space complexity of this algorithm. What else do I see in here, though? Whenever I see a loop, I have a break statement. And so I need to understand a little bit about when this break statement is gonna come into play. But my original hunch is probably that there's a case in which this is O(n) squared. Let's do something fun. Let's do this. So what I'm gonna do here is I'm going to count the number of operations that I actually performed and print that out. Okay, so how many elements are in this array? 1, 2, 3, 4, 5, 6, 7, 8. And I performed 18 operations. It's interesting. What happens if I take out this break? Oh, wait, sorry. So this is only if I'm doing the swap. Let me actually let's put this in here. And then let's take off the break statement and see what happens. Okay, so now I've got 28. So what do we think? We thought it was about n for the outer loop, n over 2 for the inner loop. This is 8, so 8 times 4 is 32. So this is close, right? Right in the roughly in the right ballpark. But that break statement makes things a little bit more interesting. It's allowing me to reduce the amount of work that I have to do. Let's try this array. Is that 8? It is. Yeah. Okay, so I put the break statement back in, but now I have an array sorted in descending order. So what does this mean? So essentially, think about it. If I take, let's say I've sorted this part of it, and I take item 6, I've got to drag item 6 all the way back to the beginning. So that inner loop is actually never going to break. Every time I have to move the element all the way back to the beginning. So that's a worst case for this algorithm. What's the best case? You want to guess? Worst case is sorted in descending order. Best case is? It's already sorted. Yeah, let's try this. Let's do 3, 4, 5, 6, 7, 8, 9, 10. Yeah, now it's O(n). Okay, so, again, we're seeing, that's one of the fun things about sorting algorithms. We see this best and worst case behavior. So worst case, O(n) squared if it's sorted backwards. Because every time I've got to take that element, where is it going in the sorted section? It's going to the front. So I've got to move it all the way to the front. Best case, O(n). If it's already sorted, I take the element, I compare it with the one next to it, and I realize that it's larger, and I stop. So every time that inner loop's gonna break out right away. Average case for this is gonna be about O(n) squared, roughly, for randomly distributed data. So this is considered, insertion sort is considered to be an O(n) squared sorting algorithm. Space complexity, so something else that we're gonna talk about. So the first improvement we're gonna make on insertion sort today is that we're gonna reduce the time complexity in the average case. And then on Monday, we're gonna talk about another variant of a sorting algorithm called quicksort that takes merge sort and improves on the space complexity, but also has some interesting corner cases to think about. So this is why sorting algorithms are so much fun to talk about. There's so many trade-offs. All right. But you've noticed here that I did not have to allocate any new array. I'm doing this in place. I've got one extra variable, and what's gonna happen right now is that every time the loop runs, this variable is gonna be allocated, but I can move it outside the loop, right? So for example, I could do this, and then I don't have to reallocate it every time. And this will still work. So, insertion sort, good in the sense that I don't have to use a lot of memory. I just have this one extra temporary variable. Questions about this? kind of thing that you will definitely see on a quiz, kind of thing you will definitely be asked about in interviews, understanding these types of trade-offs. Questions before we go on? Awesome, okay. So, brief, oh, I have another table with this, okay. So here's the thing. O(n) squared, we can do better than this. We can do substantially better, actually. I don't know if you do this in 173 or not, but you can prove, actually, that a sorting algorithm, an optimal sorting algorithm should have no worse than O(n) log n behavior, even in the worst case. So an optimal sorting algorithm, even if I design the worst input for it, it's O(n) log n. Good sorting algorithms, particularly the ones that you actually find implemented in real programming languages, do even better than that in common cases. So if the data is already almost sorted, we should be able to do O(n). So for example, timsort, which I mentioned a couple times, which is now implemented in Python and Java and probably some other programming languages, one of the reasons why it's an improvement on these sorting algorithms is because it does very close to O(n) in the common case where the data is already almost sorted. So there's a lot of times when you're programming where you're taking two arrays that are almost sorted and you're merging them together, or you're resorting an array that's already almost sorted. So large portions of it are sorted and there's one or two elements that are out of place. In that case, timsort is very close to O(n). Okay. So, brief digression about Java generics. This has nothing to do with sorting, but I wanted to show it to you because it's important. It's important for your continued understanding of how to program in Java. It's also important for MP5. So, lists, one of these fantastic data structures, incredibly useful. Here's the problem with the lists as we've used them so far. So this is what I showed you on Wednesday. I'm creating a new array list. I'm adding an object to it, okay? So I'm adding a string. What comes out if I use a list this way, when I do get, is not a string. So if I try to run this, what's gonna happen? Yeah, so this doesn't work. Why not? Who can explain what's happening to me? So this list can store any Java object. What happens? It's returning an object, and the reason is when I add something to it, that object is being upcasted to a Java capital O object. So when I add the string, the list implementation is converting it to an object. Then when I retrieve it, it's an object, not a string. So if I change this to object, then it will run, but now what is it? Now I would have to downcast it. Here's the other problem with this. Watch this. So now I've got a list that has strings in it, but also integers. And so if I use a list this way, it's great in the sense that I can put anything into it. But it's terrible in the sense that I have no idea what that list stores. And remember that and this is a nice time to recap something from previously in the class. One of the evolutions of language design is I try to change runtime errors into compiler errors. So for example, you may have something in your documentation that says this list should only have strings in it, but then you might pass a reference to the list to a function that your partner wrote or one of your colleagues, and they may put crap in it that's not a string. And so you can do this. I can say, I can downcast it, and this will work if it's a string, but what if some joker puts stuff in there that's not a string? Now I'm in trouble. So how do I fix this problem? Essentially, I want to take this runtime error and turn it into a compiler error. But I also don't want to lose the generality of this list. I still want the list to be able to hold any type of object. So in Java, this is done with a feature called generics. You guys have already seen this if you started working on MP5. So here's how we typically allocate, create, and refer to a safe list in Java, right? So I've got this new piece of syntax, which is I have brackets around a type. What does this mean? This tells the compiler that this list is going to store objects of type integer, or anything that descends from integer. So I can put anything into this list as long as it's either an integer or a child of integer, a descendant of the class integer. Down here, what I'm telling the compiler is, I'm gonna use this to store strings, or anything that descends from string. In Java, string is a final class, so it doesn't have any descendants. So now, the nice thing about this is, first of all, what comes out of the list is a string. So, and actually, this will work, but let me fix this. So I've got the angle brackets over here in my interface type, I have the angle brackets over here. So this says I'm creating an array list that's gonna store strings. Now I can add something to it that's a string, and when I retrieve the item, I don't have to downcast it unsafely. The compiler will also prevent me from putting anything that's not a string into this list. So for example, the code on line 10 is gonna cause a compiler error. Let me just pause because this is a little bit confusing. We just started using a slightly different backend for these examples, and right now, clearly the line numbers here are totally wrong. The person who maintains this project has fixed this, but I haven't applied the patch yet. So this line number is incorrect. But what's happening here is this line here on line 10, I've told the compiler I'm gonna use this list to store strings. I've tried to put an integer into it, and the code doesn't compile. If I remove this line, it works fine. So that's all I'm gonna say about generics for today. We are gonna come back and talk about generics. We'll show you a little bit of how you can use generics in your own classes. It's incredibly cool. But again, this feature is designed to create safe instances of classes that can operate on arbitrary objects. This is the reason you guys have been asking about this error you've been seeing. It says, your code uses unsafe or unchecked operations. This is why. Because there are interfaces. We can also have a generic interface. There are interfaces and various Java objects that we should be using generics on that we haven't been yet, and that's why that error message has been coming up. Again, we'll come back and talk about this more, but for now, this is the correct syntax to use whenever you create a list. You say, I want a list that stores strings, and I can create an array list of strings, I can create a linked list of strings. All of these list implementations are themselves parameterized by the type of object I want to use. And this allows the compiler to check to make sure that I'm not doing something with that list that I should. Okay, great. So now let's talk about our next, return to sorting now. Let's talk about our next sorting algorithm. So the next sorting algorithm we're going to discuss is called Mergesort. And Mergesort is based on this nice feature of arrays, which is that if I have two arrays that are already sorted, so in this case, I've got an array on top, 1, 8, 9, 12. I've got an array at the bottom, 2, 5, 7, 10. If I have two arrays that are already sorted, I can merge them in ON. How do I do that? Well, I look at the front of the two arrays, say which one is smaller. In this case, 1 is smaller, so I grab 1. Then I look at the front of the two arrays again. I say which one's smaller? 2 is smaller. I grab that. I look at the front of the two arrays again. I say which one is smaller? 5 is smaller. And I keep doing this. I'm not necessarily going to get items back and forth. I'm just going to keep taking whatever's the smallest item. I just keep doing this over and over again until the arrays are empty, at which point I've merged them. So I started off with 2 sorted arrays, and I'm left with 1 sorted array. Nice thing here is that I only ever have to look at the front of the 2 arrays. I never had to scan the whole array. I just look at the front. And so at any given step, I compare the 2 items at the very beginning. I pick the smaller one. I move that one into my array. I keep doing this over and over again. When I'm finished, I have a larger array, contains all the elements from the smaller arrays in sorted order. So let's implement this. This is one of those things that I practice before class because it's actually a little bit tricky to do. So let's create an array that we're going to use to store our merged values. How large does that array need to be? It needs to be large enough to hold all elements from the first array and the second array. So now I'm gonna, and there's multiple ways to do this, but I'm gonna loop over this large array. I'm gonna use a index called merged index, but I also need to keep track of where I am in the two smaller arrays. Okay. Can we, I need to focus. Can the whispering stop? Thanks. This is tough. All right. So I've got two indices into the first and second array. And what I want to do is I want to essentially be pulling things off one at a time, depending on which one is smaller. The problem is I have these corner cases to handle, because it's possible that I run out of elements in one array or the other array. So here's how I'm going to handle that. First thing I'm going to do is I'm going to say if first index is equal to first.length. What does that mean? It means that I've run out of elements in the first array. So where should I get the new element from? Second array, right? So I'm going to say merged index is equal to second index. And then I need to bump my second index. I have a similar case if I'm out of elements in my second index. Yes, thank you. So in this case, I'm going to take out of my first array, and I'm going to bump the index of my first array. So now if I get here, I know that I haven't run out of elements in either array, and so I can safely compare them. So I'm going to say if first index is less than second index, what do I do in this case? So now I'm comparing the elements at the front of both arrays. If the one in the first array is smaller, what do I do? I'm sorting these in ascending order. It's similar to one of the conditions you guys already have seen. So if the front of the first array is smaller than the front of the second array, which array do I take the item from? The first array, yeah. So I say merged index is equal to first index, and then I bump first index. I told you this was gross, sorry. It's just how this particularly is. Okay, now my fourth condition finally, so if I've gotten all the way here, I know that the item in the front of the second array is either greater than or equal to, or less than or equal to the one in the first array, and so that's the one I'm going to use. Okay. Now I'm going to return my merged array. Let's see if this works. Boom. Okay, good. Yeah, like conceptually this is not hard. Once you start working it out with actual Java code, it gets a little bit more gnarly. But I want to point out something about this. What is the runtime of this algorithm? Well, what do I see inside the loop? First of all, I see a loop. The loop's over the array. So it's ON in the size of the combined array. But what do I have in here? Do I have any break statements? No, I've got to fill the whole array. All of these operations are O1. They're just array lookups. I started to rewrite this last night using array lists because I thought it would be good practice, but then I remembered that array lists sometimes have, different lookup costs depending on what I'm doing. So I felt like it was best, even though it's a little uglier, to show you it using arrays, because we know that this operation on line 9 is just an array lookup and an array set. Those are both constant time, incrementing a variable constant time. So I've got an ON loop with a bunch of constant time operations inside of it. So this merge step is ON. Worst case ON, best case ON, average case ON. Fantastically predictable. Yeah, there are actually some optimizations I can make here that you can probably observe. But actually, not really. I mean, so what can I do? Right, well, as soon as I run out of elements in one array, I know that I just need to fill it with the rest of the other array. So I can make this a little bit simpler, but I still have to copy everything into the merged array. So it doesn't really help me that much. Okay, worst case, best case, average case. What about space complexity here? I know it's not on the slide. What did I have to do to get this thing going? I needed a new array, yeah. So I'm not doing this in place. I actually have to create a whole new array that's the size of both arrays I want to merge and then fill that. So that's something to keep in mind when we talk about merge sort. Okay, but how do I turn this into a sorting algorithm? Where do those sorted arrays come from? I started that with 2 sorted arrays of size 4, but where did they come from? You know, yeah, okay, you might be thinking, fine. I've got 2 already sorted arrays. I can sort them in ON, but why does this help? How am I going to use this? Remember something about arrays that's interesting. Every contiguous subarray in an array is an array. So this larger array is composed of 2 arrays of size 4. The one in front of itself composed of 2 arrays of size 2. This is composed of 2 arrays of size 1. What's really interesting about this array from the perspective of our sorting algorithm? An array of size 1, what's nice about it? It's already sorted, yeah. So I can break this into smaller and smaller pieces, and what I find is that if I do that enough, I start with a sorted array. So what I'm gonna do in merge sort is I'm gonna take 2 sorted arrays of size 1, I'm gonna merge them together to get a sorted array of size 2. Then I'm gonna take 2 sorted arrays of size 2, and I'm gonna merge them together to get a sorted array of size 4. And I'm gonna take 2 sorted arrays of size 4, and I'm gonna merge them together to get a sorted array of size 8. I'm gonna keep doing that. So at every step, I've broken the problem down, like I typically do with recursion, into these small pieces that are already sorted, and now I can reassemble them together in ON time at each step. So just as a reminder, we make the problem smaller by breaking the list or the array into smaller subarrays. The smallest subproblem is an array of size 1, which is already sorted. And how do I combine the results? I use my merge function. So this is where we'll stop. We'll come back and implement this on Monday, but let's walk through this. This is just another recursive algorithm, so we're gonna apply the same strategy that we typically do. Base case, we've broken it into an array of size 1. That array is sorted, so we're done. Recursive step, split the array into 2 equal parts. Now, in reality, I don't always start with an array that has a size power of 2, and so at some point, I may end up with an odd array, and so I've got to split it into, like, you know, I mean, it's gross, but it works, right? I have an array of size 5, I split that into 1 array of size 2, 1 array of size 3, right? I have an array of size 3, I split that into 1 array of size 2, 1 array of size 1. The array of size 1 is already sorted, the array of size 2 gets split 1 more time. So I can handle odd values. How do I combine the results? I merge the 2 arrays using this merge function that I just wrote. Okay, so next time we're gonna come back. If you were furiously trying to write down the merge function, it's right here. This is a different implementation of it, use some different notation, but still works, same thing. And when we pick up on Monday, we will finish this by actually doing the merge part of merge sort. And then we'll talk about the runtime. Okay, let me fast forward to today's announcements. So the early deadline for MP5 is on Monday. We have office hours as usual this weekend today. Please get started. There is a little bit of non-trivial work you have to do on MP5 to get to the early threshold, all right? I have office hours as usual today. Come by if you want to chat. Otherwise, I hope you guys have a fantastic weekend. I will see you on Monday.